So this is what we had last time. We basically talked about the black body radiation, sigma T to power 4. This is watt per meter square. So you multiply it by the area. So this is called, this number, sigma T to power 4, this is basically the EP2, the black radiation of surface 2. And this sigma T1 to power 4, this is called EP1. You basically say this is the emission of a black body at T1. So we said if you multiply this EP by area 1, that become watt per meter square times meter square. That's the watt. This is how many watt are leaving that surface. Leaving surface 1 everywhere. Leaving surface 1 and going to surface 2 and 4 and 8 and 9. That's the total leaving surface 1. So now if you're interested in getting just the heat transfer between those two guys, 1 and 2, then you need to say, well, how much of surface 1 is going to specifically to surface 2? And so that's basically multiplying all the radiation leaving 1 time F12. By definition, this is a fraction. This number, if it's like 30%, then you are saying 30% of this is going toward 2. All right? And then the same thing over here. This is the total radiation leaving 2 multiplied by the fraction going to 1. And when you subtract those two guys, then that is the net going from 1 to 2. So if I'm sending 100 watt toward you, and then you are sending me 80 watt, then the net flux between the two of us is 20 in one direction. And that 20 will basically keep increasing the temperature of the other guy unless someone else is cooling him and maintaining him at that temperature. Right? Very good. So that was for a black body. So now let's look at the gray body, because that's what all the surfaces we deal with will be. We will deal with gray body, not black body. So what's the difference? The difference is, one, he will not radiate black body radiation. He will radiate epsilon multiplied by this. So if this temperature is sitting at Ti, his black body radiation is sigma Ti to power 4. But because he's not a black body, he's a gray body, which is idealization of a black body, or sorry, idealization of a real body. So you would basically say it's epsilon sigma T to power 4. Again, this is per unit area. If you want to know how much exactly watts, you multiply that by the area. Right? As a black body, you would basically just radiate this, the sigma T to power 4. But for a gray body, he also reflects some. Okay? So out of the instant radiation on him, G, coming from everywhere, he will radiate rho G. It's kind of reflection. And the two of them, if you add this plus this is the total leaving you. This is called the J, and it's radiosity. And this page will look a little bit, to be a little bit puzzling, but I promise you in the next slide things will be really easy once again. Okay, so just hold on for actually 2 more slides, this one and the next slide, and then the problem of radiation become very easy after that. We will have it as if it was like a conduction problem in the first 2 chapters. Remember when we had T and T, and then they had resistance between them, and all we did was the Q is T minus T over the R. That's what we did in conduction, right? T minus T over the R. We will turn this problem into also 2 things. It's not going to be T, but 2 things and the resistance between them. And the Q would basically be those 2 guys divided by the resistance between them. Okay? The 2 guys that we had in conduction was T and T, T1 and T2 divided by the resistance. In radiation, it will actually be this guy, the radiosity. That's why we have to understand what this radiosity is. So if you want to calculate the heat transfer by radiation, you need to know the J and the J of the 2 surfaces, and you divide over, so J1 minus J2 divided by the resistance between them. That would be the radiation heat transfer. That would be the Q that the problem will ask you about in the final. Okay, so you have to have your hand on the J and the J. So what is the J? Again, it's this guy plus this guy. So he's adding them. See, look at that. epsilon EBI plus rho I GI. He's saying that if this surface is I having GI falling in it, and his reflectivity is rho I GI, then at the end of the day, this would what would come out from him. Two things will leave: epsilon I EBI plus rho I GI. Okay? And what he did here is he realized that why rho I is 1 minus epsilon I for a free quiz.
Because rho or alpha I plus rho I equals 1 and epsilon I equals alpha I.
Well, you just read that from the screen. I want more explanation. So why?
You taken
Why? If you explain this to me, you will get a free quiz. So why this is 1? Why this guy plus this guy is 1?
so this is
He's getting a free quiz.
it's an opaque surface.
Excellent. And you had your free quiz. So because tau I is 0, assuming we are doing opaque surface, which is most of the problem is, what's left? It's either you absorb or you reflect or you transmit. So if you kill the transmission, nothing goes through you, then it's only you absorb or you reflect. Right? So alpha I plus rho I is 1. But he didn't say that rho I is 1 minus alpha I. He said it's 1 minus epsilon I. Well, that's because for gray surfaces, epsilon I equal alpha I. So what you absorb, your absorptivity is also your emissivity. That's for normal surfaces. So of course, I told you last time that that would be horrible for a solar collector, because you want him to absorb every single sun ray coming toward him. You want his alpha to be really high, but you don't want his epsilon to be high. You don't want him to radiate. So that's why they have those coatings, selective coating that they paint solar collector with, in order to make their alpha and epsilon huge difference between them. Alpha very high, epsilon very low. So he grabbed the heat, but he wouldn't let it go. Right? But for normal surfaces, then alpha I equal epsilon I. All right. So this is the J. This formula is very hard to memorize, but it will get much easier than this. Right? But basically, this is the JI. Right? And you can basically saying here, you can see that if epsilon I is 1, when would that happen? Epsilon I is 1, that's when black body. Then this would be 1 minus 1. Nothing will get reflected. Why nothing will get reflected out of a black body? Because they absorb everything. It's like a black hole, but not with gravity. It's black hole for radiation. He absorbs everything, right? And he radiates with EBI. Not a fraction of it. No, the whole thing. The sigma T to bar 4. You get the whole thing. So he's basically saying for epsilon equal 1, this will fall down to this. GI become EBI. But if epsilon is not 1, if you are not a black body, GI would be not, it will not be EBI. It will be bigger or smaller? Excellent. Excellent. J would be smaller than EBI. So you have the black body radiation, but your epsilon kind of a resistance to radiation. Kind of basically tell you that no, you will not be radiating like a black body. Your J leaving you would be much lower than your EBI. And so that's where the concept comes, that there must be some kind of resistance on the surface that's related to that epsilon, that lower J from EBI. If there is no resistance, J become EBI. Your radiation is sigma T to bar 4. Congratulations, you're a black body. But if your epsilon is less than 1, there will be a resistance that's lowering your J. And we can see it in front of us right now. We can see this resistance. Can anyone see it? Can anyone have a clue how to get it? What is the resistance that's lowering J from EBI? Can you put your hand on it or your eye on it? here, this equation basically tells us that J is not EBI. There's a difference between them. If only we can put basically J in one side, EBI on the other side, we can see the difference between them, right? So here, that's basically his trial to do this, right? So this would be the resistance at the end, and we'll see how he did that, all right? This is the resistance that will become 0 if epsilon is 1, right? Imagine if epsilon is 1, it will be 1 minus 1 over 1. It will be 0, right? And then J become EBI. But if epsilon is less than 1, this will be a number. 0.1, I don't know, but it will be a number. And therefore, J would be smaller than EBI. The Q would be EBI minus J over that distance, over that resistance between them. Okay, yes?
Can epsilon be greater than 1?
Can epsilon be greater than 1? No, nothing can radiate more than a black body. Okay, that's the Carnot cycle of radiation. Okay, nothing radiates better than a black body. All right, so he's basically saying that then let's actually think there is ABI and there is GI, there is resistance between them. We don't know it yet. We just try to find out what is that resistance. Okay, and then he's saying, well, the Q then would be the Q radiating out of that surface would be the difference between, remember the surface actually had J falling into it, all right, and leaving was, look at the previous sketch, G was coming and leaving is, what's the name of those two guys together? J. So he's saying that, well, the radiation leaving that surface then, if you want to find out that surface sitting at Ti, and we had the surface, he had an emissivity of epsilon I, okay, and you got area I. If you want to figure out how much Q he's really radiating, Q dot I, how much is responsible for radiating, it will be the difference between those two guys. So J minus G. What's leaving minus what's coming. Okay, that's his own radiation.
There are different levels of black body. Like, I understand, the radiation's one for black body, but there's different types of black. I mean, compared to like a big black tar, compared to like the black piece of paper or something.
So that black body is actually nothing in real life. This is the idealization of how a perfect emitter. Okay, the tar will not be a black body. Not everything that's black have epsilon equal 1. Okay, this T-shirt doesn't have epsilon equal 1. All right. So back again, we want to calculate this Qi, and so he's basically saying it's J minus G. What's leaving minus what's coming, and it's per unit. Those guys is the unit for here is watt per meter square. So that's why he's multiplying it by meter square so that he can get the G. And then that G from here, 1 minus epsilon, he's getting it from this equation. He will take this G and he will plug everything over here. And that's why he get this. You see that? If I would, from this equation, if I would like to put my hand on the G, I would say, well, it's GI minus epsilon I ABI, right? That would be 1 minus epsilon I GI. All I did was I sent this to the other side. And then I divide over 1 minus epsilon I. And I cancel this guy. This is my GI. J minus this over this. And J minus this over this. Right? And then he take the J out, and basically the equation boiled down to this. Right? And so then you could think about, well, this, if I put this under here, so that the equation would look something like this, then the Q leaving the surface is EBI minus JI over RI, where RI is basically 1 minus epsilon I over AI epsilon I. So this is basically kind of the surface resistance to radiation. The Q is EBI minus JI over this. Okay? Very good. Again, he's saying that if epsilon I is 1, this resistance will be 0, and GI will be exactly ABI. So, what we have seen so far is a black body would radiate with sigma T I to power 4. His GI leaving him, watt per meter square would be his GI. Okay? It doesn't really matter what will fall on him. He will absorb everything and he will radiate with his own temperature. His J is basically just his black body radiation. Right? And so his QI will get divided to surface 1, 2, 3. How much of that Q will go to surface 1 and how much of that Q will go to 2 and 3, that will depend on the, or basically yes, the angle of course and the geometry, but at the end of the day we call this the view factor, the Fi1 and Fi2 and Fi3. So out of all those QI, leaving the flame in the side of in the corner of the room, how much of that heat leaving that flame will hit the curtain of the window and the carpet in the window, and that's the view factor of each one of them. The ceiling will get 30%, so it must be that if flame ceiling is 30.3, and the curtain will get 10%, it must be that if flame curtain is 0.1, right? So we will get the view factor from the tables, and out of that Q will basically say, well, QI1 and QI2 and QI3. And if you are a gray body, you will have this surface resistance that will lower your J than your black body radiation. It will be much lower, right? And the Q leaving you would be basically this minus this over this resistance, all right? And how much will go to 1 and 3, and this again would be the view factor for each one of them. So now one of you should suspect a problem here, or something is not comfortable. What is it? Anything that you don't buy or you think it's gonna give us trouble in this scenario? So I'm asking for QI. And of course I will give you the temperature and the epsilon. I mean, give you the surface property, and you will work your measure to get the F1, 2, and the Fi1 and the Fi2 and the Fi3. And are you ready to calculate the Q leaving surface I and going to each one of those surfaces, or not yet? Any problem you expect? For a free quiz? So the temperature is given, the property is given. You will work all through the table looking at the geometry, you will get those fractions. At the end of the day, I'm asking you to calculate the Q leaving surface I and hitting surface 1 and leaving I surface 2. And what's wrong with using this formula to do that? Don't have the area? No, you have the area. I'll give you the area. What else? For a free quiz. You don't have the J or the Q. One equation, two unknown. How's that gonna work? Yes, the Q is the black body radiation that I know the temperature, minus J, but how much is the J? And if I don't know the Q, how can I get the J? And if I don't know the J, how can I get the Q? Right?